Welcome once again to this YouTube channel. In this particular video, we are going to be solving the Cambridge IGCSE Chemistry question paper 4 extended, and it's May June 2023, and the paper variant is 43. So we're going to be solving these questions. I want you to follow through as we do them together. Okay, so the first question here says that some symbol equations and word equations A to J are shown, and you're expected to use these symbol equations to answer questions A to F. All right, so let's begin with the first question there. It says which of them is an equation for photosynthesis. Now you recall that photosynthesis is one of the reactions that gives off hydrogen to the environment. So just look at your equation. Which of them is giving off hydrogen? You see that it's J, because you can see hydrogen liberated to the environment. And that should also remind you that it's simply a form by which the green plants manufacture their food in the presence of sunlight and chlorophyll. So in this case, J is going to be the answer. So our answer here is J. Now the second one says which of them is an addition reaction. Now addition reaction happens to be one of the reactions undergone by the alkenes. So alkenes generally undergo addition reactions sometimes with the halogens. So look at where we have an alkene from equations A to J. You see that in D we have an alkene, that's propene, reacting with bromine to form 1,2-dibromopropane. So this is an example of an addition reaction. Next one says a precipitation reaction. Now a precipitation reaction is a reaction that forms a precipitate, and we all know what a precipitate is: an undissolved solid. So if we look at all the equations we are given here, we see that equation B has what we call the chromium 3 hydroxide precipitate, which is green in color. So that is the answer to that. The next one says which of them is an incomplete combustion. Now incomplete combustion produces two products, carbon monoxide and water, so H2O. So these are the products of incomplete combustion of a hydrocarbon, while complete combustion gives you carbon dioxide and water. So that's the difference between the two of them. So look at your equation. Which of them involves the hydrocarbon that undergoes incomplete combustion to produce this? So if you look at everything, you see that G is the perfect answer to that. So in this case, we just write the G. Okay. Now the next one talks about a displacement reaction. Now a displacement reaction is simply a reaction between a more reactive element displacing the less reactive one. So if you look at this equation, all the equations that you are given, if you look at F precisely, you see that chlorine reacts with aqueous potassium bromide, and then it displaces bromine from aqueous potassium bromide and takes the place by forming aqueous potassium chloride. So that's a simple example of displacement, because chlorine is more reactive in this case than the bromine. So we have F in that answer. And then the last one says a substitution reaction. Now, substitution reaction is one of the reactions of the alkanes, especially with the halogens. Okay, so in this case, you look at an alkane there, which is methane, reacting with an halogen chlorine to form chloromethane and hydrogen chloride. So that's an example of a substitution reaction. And remember that reaction it needs to take place in the presence of the ultraviolet light. Okay, because a photochemical reaction. All right, so every of these reaction has a name at some point, so you need to get used to these reactions and what they represent. Like the first reaction here, A now is simply a neutralization reaction, because it involves the acid, the proton from the acid, and the hydroxide from the alkali to form water. So we also have E, sorry, E, which is simply catalytic cracking, or say thermal cracking, because there is a break of a larger hydrocarbon, breaking of a larger hydrocarbon to form the smaller ones. Okay, so you just have to get used to some of the reactions and you'll be able to answer questions like this. Okay, let's move forward to the next questions. Now the symbols of the elements in period 3 of the periodic table are given here. And then you are expected to use these symbols to answer the questions as usual. So the first one is, which of them is present in the purified bauxite? Now remember, in the extraction of aluminium, the bauxite is purified, and the extraction of aluminium bauxite is also known as aluminium oxide. So this is the purified bauxite. So which of them suits into the list we are given? You see that aluminium is the perfect answer to this. So it is one of this is the mineral ore for the extraction of aluminium. All right, that's purified bauxite through the process of electrolysis. Now, which of them contains atoms with a full outer shell of electrons? Now, when we're talking about full outer shell of electrons, we're simply referring to the noble gases. So look at your periodic table, look at which element falls under where we have the noble gases. You realize that it's simply argon. So in this case, argon is a noble gas, so it will have full outer shell of electrons, and that's what makes them unreactive. Which is used to kill microbes in water treatment. Now, remember, from the knowledge of treatment of water, chlorine is what is used to kill the microbes. Which one forms an amphoteric oxide? Now, when we talk about amphoteric oxide, we're talking about oxides or compounds that can react with an acid or a base. So, and we give about two examples of such. Actually, we have about two of them: aluminium oxide and zinc oxide. So we do not have zinc in this list, so we have aluminium. So aluminium will still be the answer here. Which of them forms an oxide which causes acid rain? Now, two likely element forms oxide that causes acid rain: sulfur and nitrogen. So their oxides is what react with water to form acid rain. Now, we do not have nitrogen in the list, but we have sulfur. So sulfur will be the answer here. Which one has an oxidation number of -1 when it forms a compound with hydrogen? So which of them has an oxidation number of -1? So all the metals are excluded. So this is not there, this is not there, this is not there. And the noble gas, of course, will not. So which element do you think has an oxidation number of -1? For it to be an element with oxidation number of -1, that means that element has received just one electron. And the likely element to display such property are simply the halogens. The halogens are elements that only need one electron to have a full outer shell of electrons. So in this case, which of this list has the halogen there? So chlorine is the halogen. So chlorine will be the answer here. All right, so I believe that we have answered those questions. So let's go to another question now. The relative atomic masses of the elements can be calculated from the relative masses of isotopes and their percentage abundances. So identify the isotope to which all relative masses are compared. Now, all relative masses are compared to the carbon-12 isotope. So carbon-12 isotope. Every isotope is compared to the carbon-12, or every relative mass of an element is compared to the carbon-12 isotope. Now, table 2.1 shows the relative masses and the percentage abundances of the two isotopes in a sample of magnesium. So in the first isotope, we are given the relative mass and we are given the percentage abundance, and also a second isotope, relative mass and the percentage abundance. So we want to calculate the relative atomic mass of magnesium to 1 decimal place. So relative atomic mass of magnesium to 1 decimal place. So to get the relative atomic mass, let's title it RAM. Okay, it's going to be, what is the percentage abundance of the first isotope? So 85 over 100 multiplied by the relative atomic mass of the first isotope, 24, plus relative percentage abundance of the second isotope, 15 over 100, times the relative mass of the second isotope, which is 26. So if you use your calculator in this case, use mine here, 85 times 24 divided by 100, so that's 20.4. Okay, so we're going to have 20.4 here. And then we move to the next one, which is 15 times 26, all divided by 100, we have 3.9. So for the second isotope is 3.9. So we add up the two values, we have 24.3, and it has to be in 1 decimal place. So we simply write 24.3. So that is the relative atomic mass of the magnesium to one decimal place. So that's how you calculate any question that involves this angle of questioning. Now, moving forward, there's a question here that says an ion contains 10 electrons, 13 protons, and 14 neutrons. State the nucleon number of the ion. Now, the nucleon number is simply the same as the mass number. So remember that the formula for the mass number is simply the number of protons plus the number of neutrons. So in this case, this is the nucleon number now, the mass number. So the protons here is 13 and the neutrons is 14. So if we add both of them up, we are having 27. So the nucleon number is 27. Okay, identify the element that forms this ion. So for you to identify the element that forms the ion, look at the proton number, which is 13, then open your periodic table and look for an element with atomic number 13. And you check that, you should have aluminium. Okay, so aluminium should have that atomic number. Okay, so remember that nucleon number is the same as the mass number. Alright, so we move to another question here. It says magnesium forms ionic compounds. Magnesium reacts with fluorine to form the ionic compound magnesium fluoride. The electronic configurations of an atom of magnesium and an atom of fluorine are shown in this figure. So we can see the electronic configuration of magnesium here and that of our fluorine here. So what I would like us to do is to write out the configuration quickly. So that's 2 electrons in the first shell, followed by 8 electrons, followed by 2 electrons. Okay, and then for the second one, we have 2 electrons, followed by 7 electrons. Alright, so it says the ions are formed by transfer of electrons from magnesium atoms to fluorine atoms. Remember that it's an ionic compound, right? And of course, for it to be an ionic compound, there must be transfer of electrons from the metal to the non-metal. So we have to complete a dot and cross diagrams in figure 3.2 to show the electronic configuration of one magnesium ion and one fluoride ion. So, and we are expected to show the charges on the ions. Now in this case, we expect magnesium to give out 2 electrons because it has 2 electrons in its outer shell. So what we are expected to draw just one magnesium ion and one fluoride ion. So we have the first shell, which is 2 electrons. So we draw the next one, which has to be 8 electrons. So 1, 2, 3, 4, 5, 6, 7, and 8. So this is the magnesium ion after it has lost 2 electrons. So what I need to do is to include a 2 plus, because magnesium is giving out 2 electrons. Now, since we have just one fluoride ion, so the one fluoride ion is going to receive one of the electrons, while the second fluoride ion will receive the next electron. So to draw the fluoride ion that is receiving the electrons, all I have to do is to draw the 7 electrons first. So 1, 2, 3, 4, 5, 6, and 7. And then I'll draw the 1 electron that was received from the magnesium this way. So with this way I've drawn, and I can just represent this place as the negative. Okay, so this is what I've expected to do. So we could also draw the second fluoride ion and then show how the second magnesium electron goes to it, but the question doesn't ask us to do so. Now deduce the formula of the magnesium fluoride. So for us to deduce the formula of the magnesium fluoride, we use what we have obtained here. So we have magnesium, and the charge of magnesium is 2 plus. And then we have the fluoride ion, and of course it's minus, which is more like the -1. Okay, so the idea is this, that they exchange oxidation numbers excluding the charge. So we are going to exchange oxidation numbers and we are going to exclude the charge. So what will happen is the 2 will come all the way down here and the 1 here will come all the way down here. So this is the positions they will occupy. So if the 1 in fluorine comes all the way down to magnesium, it becomes just Mg. Okay, and then the 2 in magnesium goes all the way down here, it becomes F2. So this is the formula of magnesium fluoride. Now, when solid magnesium fluoride is dissolved in water, it forms a solution that conducts electricity. Now, state one other change that can be made to solid magnesium fluoride to allow it to conduct electricity. One other change that can be made is simply melting. So melt the magnesium fluoride and it will conduct electricity. So this is one other chain that can be adopted, all right, apart from dissolving it in water. All right, so that's for that question. So we go to this question here. It says silicon tetrachloride and silicon oxide, silicon 4 oxide rather, are covalent compounds. Now complete the dot and cross diagram in figure 3.3 to show the electronic configuration in a molecule of silicon tetrachloride, and we are also expected to show only the outer shell electrons. So now let's write the configuration of silicon. Now silicon is 14, so we're expecting 2, 8 and 4. And then for chlorine, which happens to be 17, okay, the configuration will be 2, 8, 7. All right, so we are going to draw only the outer shell electrons in this case. So remember that this configuration is gotten by using the atomic number. All right, so let's draw that of chlorine first. So 7 electrons on the outer shell. So we have, let's use the cross for chlorine. So we have 1, 2, 3, 4, 5, 6 and 7. So this is the first chlorine. We do this for the second chlorine. So 1, 2, 3, 4, 5, 6, 7. We do it here again. 1, 2, 3, 4, okay, 5, 6, 7. All right, so that's for the other chlorine. And the last chlorine, 1, 2, 3, 4, 5, 6, 7. All right. So remember that when you are filling it, you have to fill all the shells first before you begin to pair. So so just doing that too. So we fill first before we pair. All right, now that we filled chlorine, so let's fill that of silicon now. Remember that silicon has just 4 electrons. So the first silicon, we represent it with the dot diagram. So we just have 0 here. So this is the first silicon, second silicon, the third silicon, and the fourth silicon. So this is what you're expected to do in this case to get the 2 marks. Now, the next question says that the melting points of silicon tetrachloride and silicon 4 oxide are shown in table 3.1. You can see that the melting point of silicon tetrachloride is -69, and the melting point of silicon 4 oxide is 1710. That's a lot of gap between them. So silicon tetrachloride has a low melting point because it has weak forces of attraction between the particles, and that's why it has a low melting point. So name the type of particles that are held together by these weak forces of attraction. So the type of particles are simply the molecules. So molecules are the types of particles that are held together. So molecules are the particles that are held together by the weak forces of attraction. Now explain in terms of structure and bonding why silicon 4 oxide has a high melting point. Now silicon 4 oxide has a high melting point. Number one, because it has a covalent bond. So it contains a covalent bond. It contains a covalent bond. But remember that silicon tetrachloride also has covalent bond. But the major thing is we have to establish that there is a presence of covalent bond. But the covalent bond in silicon 4 oxide is a strong covalent bond. So it's a strong covalent bond, or we say it's a giant covalent structure. That is the difference between the silicon 4 oxide and the silicon tetrachloride. Okay, it is a strong giant covalent structure. Okay, so in the case of silicon tetrachloride, it's equally a covalent bond. Okay, but in that of silicon 4 oxide, it's a covalent bond with a giant covalent structure. So the bonds are stronger in silicon 4 oxide than in silicon tetrachloride. Okay, so that is for that, and that's why it has a higher melting point. Now we go to the next question, which is question 4. Hydrogen is produced by the reaction between zinc and dilute sulfuric acid. The student carries out an experiment using excess zinc and dilute sulfuric acid. The student measures the volume of the hydrogen gas produced at regular time intervals using the apparatus. So this is the apparatus. There are lumps of zinc. In this case, you can see lumps of zinc, and then there is the acid, and then there is the gas that measures the gas syringe that measures the amount of gas produced. Lumps of zinc are used. Please take note of that. So the rate of reaction decreases as the reaction progresses, and then the rate eventually becomes 0. So we have to explain why the rate of reaction decreases as the reaction progresses. So as the reaction progresses, the rate decreases because the acid particles are decreasing. So the acid particles are decreasing. Remember, the acid is sulfuric acid. So as the acid particles are decreasing, of course, the rate will decrease. Or you could say that the number of particles available for collision are decreasing as the reaction progresses. So the acid particles are decreasing. Okay. Now explain why the rate of reaction eventually becomes 0. The rate of the reaction eventually becomes 0 because the acid particles, the particles of the acid have been used up. The particles of the acid have been used up. Okay, so this is the reason why the rate of reaction eventually becomes 0, because there are no particles to collide any longer. Okay, so when there are no particles to collide, the rate of reaction becomes 0. And for the first question, like we mentioned, why the rate of reaction decreases as the reaction progresses is simply that the particles of the acid are decreased. Okay, and the particles, the frequency of collisions has also decreased because there are no longer enough particles to collide to increase the rate. The experiment is repeated using powdered zinc instead of the lumps of zinc. All other conditions remain the same. So explain in terms of collision theory why the rate of reaction increases if powdered zinc is used. Now we are moving from lumps of zinc to powdered zinc. Now what does that mean? Number one, that there is an increase in surface area. So an increase in surface area. There's an increase in surface area. And because there's an increase in surface area, the frequency of collision will also increase. Okay, so since there's an increase in surface area, frequency of collision increases between the zinc particles, that is between the particles. Okay, so there is the frequency of collision increases because there's an increase in surface area. So there is more frequency of collision between the zinc particles and the acid particles. That is why the rate of reaction increases. So we have cited 2 reasons because there are 2 marks here. So it's good that you are able to give enough reasons to get the full mark. So the first reason is that when we move from lump of zinc to powdered zinc, we have simply increased the surface area. And because we have increased the surface area, the frequency of collisions increases between the particles of the zinc and acid. Now this is the next question here. It says the equation for the reaction is shown here. All right, and zinc plus sulfuric acid to give zinc sulfate and hydrogen gas. Now 25 centimeter cube of 2 mole per dm cube acid H2SO4 is added to excess zinc. So we have to calculate the volume of the hydrogen gas formed at room temperature and the pressure, and then the volume of 1 mole of any gas is 24 dm cube at room temperature and pressure. So we're expected to use the following steps. Calculate the number of moles of the sulfuric acid used. Now to get the number of moles of sulfuric acid used, remember that we are given the volume of sulfuric acid to be 25.0 centimeter cube. And we are given the concentration of sulfuric acid to be 2.00 mole per dm cube. Okay, so these are the information we have. And then remember that to get the number of moles, the formula is concentration is number of moles divided by the volume. All right, so for us to get the number of moles in this case, all we need to do is to cross multiply here, and then the number of moles will be C concentration times volume. So number of moles in this case will be concentration times volume. But we have to be careful here because the volume is in centimeter cube and the concentration is in dm cube. So it's important that we unify the units. So we have to convert the volume to dm cube. So to convert the volume to dm cube, so V will now be 25 divided by 1000, because we are converting from cm cube to dm cube. So if you do 25 divided by 1000, we're going to have 0.025 dm cube. So after the conversion, we can now do the multiplication. So we're going to have n, it will now be c. What is c now? 2 times 0.025. So if you do that multiplication, let me do it here, times 2. So we're going to have 0.05. So the number of moles here is 0.05. Now, the next question says, deduce the number of moles of hydrogen produced. Now, for us to deduce the number of moles of hydrogen produced, we have to go back to the equation of the reaction and look at the stoichiometry. Now, in this case, we see that the equation is balanced. So it means that 1 mole of zinc sulfur, the zinc and solid, is reacting with 1 mole of the acid to produce 1 mole of zinc sulfate and 1 mole of hydrogen gas. Because if you look at the coefficients of each of the reactants, we see that they all have 1, 1, 1 in front of them. So that means the mole ratio is all uniformed. Now, if the mole ratio is uniformed and we have calculated that 0.05 mole was needed here to make this reaction, possible. So if 0.05 mole was needed, therefore, since they have the same mole ratio, that means 0.05 mole of zinc is also needed. 0.05 mole of zinc sulfate was produced, and 0.05 mole of hydrogen gas was equally produced, since they share the same mole ratio of 1, 1, 1, and 1. So in this case, our answer just becomes 0.05. Remember, the reason is because they have the same mole ratio. Now, calculate the volume of hydrogen formed at RTP. Now, to calculate the volume of hydrogen formed at RTP, it's simply the number of moles of the hydrogen produced times 24 dm cube. That's as simple as it is. So just do 0.05 times 24, and we have 1.2 dm cube. So that's how to get the volume at RTP. Now, moving forward, hydrogen can be produced by the reaction of zinc with dilute hydrochloric acid. So write a simple equation for this reaction. So zinc solid, of course, plus hydrochloric acid, that will be aqueous because it's diluted. So we have the zinc solid, which is aqueous, plus hydrogen, of course, it has to be a gas. So 1 zinc, 1 zinc. So what we just need to do is to put a 2 here, and then everything is balanced. Now, this hydrogen gas has been produced here. We have to state the test for the hydrogen gas. So what do we need? We need a lighted splint. So a lighted splint is what is needed. That's the test. And then what will be the result? When you use a lighted splint, take this lighted splint near the hydrogen gas, it gives a squeaky pop sound. So when you get that pop sound, that tells you that hydrogen gas is present. As test for gases. All right, so that's for the squeaky pop sound. Now, this question is about electricity and chemical reactions. So aqueous copper 2 sulfate is an electrolyte. The electrolysis of aqueous copper 2 sulfate using inert electrodes forms copper at the anode and oxygen at the copper at the cathode and oxygen at the anode. So the first question tells us, let's look at the information before we answer the question. So the electrolysis of aqueous copper 2 sulfate. So we are looking at the aqueous copper 2 sulfate, which is blue in color, remember? And then copper is at the cathode, oxygen is at the anode. So what is meant by the term electrolyte? So electrolyte is a substance. Okay, so we are going to write an electrolyte. Please, I might not write all the information because of the difficulty in writing using this board. But let's just try. So an electrolyte is an ionic substance. Please, this is important. Ionic substance. Okay, ionic substance in the molten. So ionic substance in the molten or aqueous states that decomposes due to the passage of current. Okay, so any ionic substance which has to be in the molten or aqueous state that decomposes due to the passage of current through it is called an electrolyte. So how do you get the mark in this case? What we need in the mark guide is mention ionic substance, mention the fact that ionic substance must be in the molten or aqueous state, and then you get the full mark. So please take note of this. So when you are asked an examination to define the term electrolyte, what you need to include in your definition is, number one, it must be an ionic substance, and then it must be in the molten or the aqueous state. State the term given to the Roman numeral in the name copper 2 sulfate. So the 2 there is simply the oxidation number, oxidation, either you say oxidation state or oxidation number of copper. So the oxidation number of copper in that compound is 2. That's why it has the Roman numeral 2. State what happens to the color of the aqueous copper 2 sulfate as this electrolysis progresses. Now remember that as the electrolysis progresses, copper is produced at the cathode. So for that, the blue color of the aqueous copper 2 sulfate will begin to fade off. So we say the color, it fades off. So the color fades off, or it becomes colorless. So either of them, you'll be right. So either you say it fades off or it becomes colorless. Write an ionic half equation for the formation of copper at the cathode. Now at the cathode, there is gaining of electrons, while at the anode, there is loss of electrons. So you have to show how copper gains the electrons in this case. So we have Cu2 plus the E minus, that's the gain, that's the electron that has been gained, and then you form the copper solid. So we balance this by putting a 2 here. Okay, so this is the equation that shows that copper has this half ionic equation for the cathode. Give the formula of the ion that forms oxygen at the anode. Now, oxygen is formed at the anode. So what is that ion that is formed at the anode? For us to do that, we have to break down the process of the electrolysis. So it's looking at aqueous copper 2 sulfate. Now, this is copper 2 sulfate. This is the formula of copper 2 sulfate. So in aqueous state, that means it's dissolved in water. Okay, so for cations, that's the positive ions in this solution. Let's look at the cations. We have copper 2 plus, and we have the hydrogen ion. So these are the cations. Then the anions will become the SO4 2 minus from the salt, and then OH minus from the water. So the copper is deposited at the cathode, and then this is what is deposited at the anode. So the source of the oxygen is simply the OH minus. The electrolysis of copper 2 sulfate is repeated using copper electrodes. State what happens to the anode. Now, when you use a copper electrode instead of an inert electrode, what will happen is that the anode, which is made of copper, will dissolve. So the anode will dissolve in the solution because the electrolyte is copper sulfate. So the anode will dissolve. That is what will happen. Now, spoons can be electroplated with silver. Name the substances used as the anode. Now remember that the anode, there is loss of electron. So the metal or the ion that is losing electron will be what you want to use to electroplate. And in this case, it's simply silver. So silver will be at the anode because silver needs to lose electrons. And then the electrons lost by silver will now be used as an electroplating substance on whatever needs to be electroplated, which needs to be at the cathode, and that's the spoon. So what you are trying to electroplate will be in the cathode, while what you intend to use to electroplate should be at the anode. And then the electrolyte in this case has to contain silver. So we can say silver, a compound of silver, an ionic compound of silver can be silver nitrate. So this could be an ionic compound of silver. Alright, so state 2 reasons. Sorry about that. State 2 reasons why spoons are electroplated. So we electroplate spoons known to prevent corrosion. So spoons are electroplated to prevent corrosion. And spoons are also electroplated to improve the appearance of the spoon. So you want to improve the appearance you want to improve the appearance, that is when you apply the process of electroplating. All right, so let's go to the next question. Hydrogen oxygen fuel cells can be used to produce electricity to power cars. Petrol produces carbon dioxide and carbon monoxide when it powers cars. State one adverse effect of carbon dioxide and carbon monoxide. Now remember, carbon dioxide is a greenhouse gas, and then what it simply results into is to increased global warming, because that's one of the effects of greenhouse gases, and carbon dioxide happens to be a greenhouse gas, so increased global warming. And then one effect of carbon monoxide is that it's toxic, and therefore it could lead to respiratory problems. State one disadvantage other than cost of using hydrogen oxygen fuel cells to power cars compared to using petrol. Any other disadvantage other than cost is that the hydrogen needs high pressure. High pressure is needed to store. Okay, high pressure is needed or is required to store hydrogen. So you need high pressure to store the hydrogen. That's one disadvantage. Okay, so that's for that. Now let's go to question 6. That's a question. After question 6, we have question 7, and then that's all for this paper. So question 6 is about nitrogen and compounds of nitrogen. Ammonia is manufactured by reaction between nitrogen and hydrogen in the Haber process. And this is the equation of the Haber process reaction. So state the source of nitrogen for the Haber process. So the source of nitrogen is from air. Okay, because one of the components of air is nitrogen, about 78%. So we can get a larger proportion of nitrogen from air. So we just simply say air. Okay. State the source of hydrogen for the Haber process. The source of hydrogen for the Haber process is simply from methane. Okay, so it's simply from methane. Now, state the typical conditions used in the Haber process. This has to do with temperature, about 450 degrees Celsius, and the pressure, about 200 atm. So please take note of these conditions. The catalyst used in the Haber process is finely divided ion. So finely divided ion. And what is meant by the term catalyst? This is for 2 marks, so you have to state good points. So the first one is that it's a substance that increases the rate of reaction. A substance that increases the rate of a reaction and remains unchanged. Please take note of this. It remains unchanged. So this is how to get the 2 marks. First, you have to state that a catalyst increases the rate of reaction, and then you have to also emphasize that it remains unchanged. All right, so that's for that. Ammonia is converted into nitric acid. The first stage is the conversion of ammonia into nitrogen monoxide, and then he says the reaction is carried out at a temperature of 900 degrees Celsius and a pressure of 7 atm. The third reaction is exothermic. Using explanations that do not involve cost, explain why a temperature less than 900 degrees Celsius is not used. If you use a temperature less than 900 degrees Celsius, you will lower the rate of the reaction. So why is that done? It lowers the rate of reaction, the rate of reaction. Okay, that's why it has to be done in a higher temperature. Okay, that's why it has to be done at 900 degrees, not less than 900. Now explain why a pressure greater than 7 atm is not used. Now if you use a higher pressure, it's going to favor the side of the reaction with lesser volume. So let's look at the side of this reaction with lesser volume. We have the reactant side and we have the product side. So let's add the number of volumes in the reactant side. So that's 4 plus 5. So this is 9 volumes. Yeah. If you add this one, 4 plus 6, 10 volumes. So we are saying that when you increase the pressure, you're going to favor a side with lesser volume. So which side do you think is going to be favored? Of course, the side with lesser volume is the reactant side. So when you use the pressure greater than 7 atm, the equilibrium will shift to the left. Will shift to the left. But remember that the essence of the reaction is to have more of this product, not for it to shift to the left. So we want the reaction to shift to the right. We want the equilibrium to shift to the right. So when you use a pressure that is greater than this 7, it will simply favor the reactant and it will shift to the left. Okay, so that is why a pressure greater than 7 is not used, because we want to have more products and not more of the reactant. Right. So I believe that is understood. So in the second stage, you see nitrogen monoxide reacts with water and oxygen to produce nitric acid. And we are expected to balance the symbol equation for this reaction. Now, of course, you know what balancing actually does. You have to write out all the elements that are involved and the number of atoms on the left and number of atoms on the right. So in this case, I'll just go straight to the balancing, okay? Because this is an extended paper. So I expect most people want to take the extended paper to be able to balance chemical equations. So in this case, look at nitrogen, oxygen, and water, and then the acid. So let's try out with four of this here. So if there are 4 of this here, that means there should be about 4 of this here. So if there are 4 nitrogens and there are 4 nitrogens here, there are 4 hydrogens here. So if there are 4 hydrogens here, there should be 2 hydrogens here. Okay, so let's look at it again. 4 nitrogens on the left, 4 nitrogens on the right, 4 oxygens on the left, 4 hydrogens on the left, 4 hydrogens on the right. Now let's look at oxygen, which is the last thing we want to balance. 4 times 3, 12 oxygens on the right. Now how many oxygens are on the left? 4 plus 2 here, that's 6. 6 plus 2, 8. So for us to have 12 oxygens, let's put a 3 here. So let's see now, 4 oxygens plus 6 oxygens, that's 10, plus another 2, 12. So that makes it balanced, all right? So a student makes aqueous copper 2 sulfate by adding excess of solid copper 2 carbonate to dilute nitric acid. Write the symbol equation for this reaction. All right, so we are reacting solid copper 2 carbonate with dilute nitric acid. So what we're going to have is, this is CuCO3, of course, solid plus nitric acid, HNO3, which is diluted, aqueous. So we're going to have the copper 2 nitrate will be formed, so CuNO3 2, of course, aqueous, plus, of course, you're going to have carbon dioxide giving off as the gas. I'm going to have water equally formed, okay, liquid. Okay, so we have that as the reaction. Okay, so let's see how we can easily balance this. Let's not touch, let's look at hydrogen. Hydrogen seems to be the one not balanced here. So hydrogen 2, so I put a 2 here. Okay, so 2 hydrogens, 2 nitrogens, 6 oxygen plus another 3 here, 9. So 6 plus 2, 8 plus 1, 9. So that's just balanced. Okay, so that's for that. State 2 observations that indicate that the copper 2 carbonate is in excess. Number 1, there's a gas giving off in this reaction. So for you to know that the copper 2 carbonate is in excess, that gas will stop. The gas liberation will stop. So we can say effervescence simply the liberation of a gas. Effervescence stops. Okay, so effervescence stops. That's to show you that you have added too much of the copper 2 carbonate. And then another reason we can know is that you will have undissolved solid. So the acid will no longer be able to dissolve the solid. So we have presence of undissolved solid to tell you that, oh, we've added excess of copper 2 carbonate. That needs to go through filtration so that the excess copper 2 carbonate now becomes a residue. So those are the 2 ways or observations that you can use to determine that you've added excess of copper 2 carbonate. Now, name one compound other than copper 2 carbonate that can be used to dilute nitric acid to produce aqueous copper 2 nitrate. So it has to be a compound of copper. It can be copper 2 oxide, or it could be copper 2 hydroxide. So just a compound of copper can do the can be used to replace copper 2 carbonate. All right, so moving forward, this is the last question now, question 7. This question is about organic compounds. So this is always organic chemistry zone. Now, propane and chlorine react at room temperature, and an equation for the reaction is shown. So this is an example of a substitution reaction. And like I said earlier, the condition required for this reaction is ultraviolet light. Okay, ultraviolet light. So we need ultraviolet light for this reaction to go through because it's a photochemical reaction. Now, draw the displayed formula of two structural isomers with the formula C3H7Cl. So structural isomers means they have the same molecular formula, but in terms of structure, they vary. Okay, the way the atoms are arranged varies. So let's draw the first one, C3H7Cl. We have something like this. 3 carbons, right? 1, 2, 3. 7 hydrogens, so we can have 1, 2, 3, 4, 5, 6, 7. So we've drawn 7 hydrogens and then 1 chlorine is attached. So this is the first one. All right. So now what we can do is, since they are the same molecular formula but different structure, we can alternate this structure by moving chlorine to probably the second carbon. Okay, to make sure that they are structurally related. So we can see now, this is the second structure now. So we attach 7 hydrogens as well. H, 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 H again. Then we move the chlorine to the second carbon, which is this. So if you count the number of carbon atoms and the number of hydrogens and number of chlorine, they must be the same. But the way they are arranged is what varies now. So in this one, we can name this one 1-chloropropane because there are 3 carbon atoms. And then this one now become 2-chloro because the chlorine is on the second carbon. So 2-chloropropane. So this is a structural isomer. The same molecular formula, but in terms of structure, they vary. All right. So that's for that. State 2 characteristics that all members of the same homologous series have in common. Okay, alkenes are a homologous series of hydrocarbons. So one property we can use is they have the same chemical properties. So members of the same homologous series have the same chemical properties. That's one, and they also have the same general formula. So that's another way to identify member of the same homologous series. You could also add that they have the same functional group. So that's for that. Addition polymers are made from alkenes. Okay. So complete figure 7.1 to show one repeat unit of the addition polymer formed from butene. Now, for us to do this, let's draw butene first before we complete this diagram. So butene is an alkene, so it has this double bond, and there are 4 carbon atoms. That is why it is but2. And then the double bond is on the second carbon. So we could have something like this, right? So H and CH3. So we can see that there are 4 carbon atoms here, and then the double bond is on the second carbon atom, which is literally with 2 So we want to have show how the repeat unit of this will be when we add several butenes together. What would be just a single repeat unit? How would a single repeat unit look like? So what we just need to do is to simply do a transfer. Now, this is the first carbon atom, so this is the position. Of course, the bond is going to break to a single bond, so we're going to have something like this. So we're going to have a single bond here. All right, so single bond has been incorporated there. And then look at the first carbon atom. What are those things present there? We have CH3 and H. So we just transfer these same entities to what we have here, to the first carbon here. So CH3 and H. And then for the second one, we also have H and CH3. So H and CH3. I think that's all for that question. So first we put the single bond, and then we attach the atoms that should be there. All right. So that's for this question. Right? Now, moving forward, I think a repeat unit of a condensation polymer is shown in figure 7.2. Now, the polymer is made from 2 monomers. Okay, so of course, condensation polymers, of course, liberate, they form a compound and they liberate something. All right, so in this case, we have two monomers that have combined, and we're expected to draw the structures of the two monomers that was used to produce this. Now, how do we know the two monomers that came in together? We have to look at the polymer that was formed. And one way is to remember that there's what we call several links. Okay, so in this case, this is the link. This is where the linking occurred. So this is the link. And for us to have a link like this, okay, this is an ester linkage. Okay, ester linkage. If you remember your polymers, condensation polymers, this is what we call an ester linkage. Okay, so and remember that how are esters formed? Esters are formed when you react, when you combine carboxylic acid and alcohol. Okay, so when you combine carboxylic acid and alcohol, you form what we call esters. All right, now in this case, now we now know the two monomers that make up this polymer. Because there's an ester linkage, it means that there is a carboxylic acid somewhere and there is an alcohol somewhere. So the carboxylic acid is simply this from this left hand side. You can see that that is why we have this C double bond O. Remember, the carboxylic acid is the functional group is COOH, and then that of alcohol is simply OH. Okay, so for us to have formed this, that means the carboxylic acid came from this left. So let's draw the carboxylic acid now. So we have the COO. So what is missing is the OH. So we're going to have something like this. OH, that is here, and then we have CO, CH2, CO, OH. All right, so this is the carboxylic acid, where this is extracted from. And then let's draw the alcohol now. So the alcohol starts from here. So we have starts from this point. So we have the OH, all right, and then we have CH2C. Okay, let's just follow it the way it is here. So we have OH, CH2CH2OH. Okay, so these are the two monomers that came together. Remember, we established that since there is an ester linkage, it means, and know that esters are formed when carboxylic acid and alcohol come together. So that is how we're able to form this. Now that we know how to get that, it's now left for us to name the carboxylic acid and the ester and the alcohol. So in this case, this is propan, because there are 3 carbon atoms. It is propan 1, 3 dioc. So this is propan 1 and 3 dioc, and then this one is ethane 1, 2 diol. So these are the two monomers that came together to form the polymer. Name the type of condensation polymer in figure 7.2. Now, when this kind of polymer is called a polyester, because it leads to the formation of an ester linkage. So it is simply referred to as a polyester. Name 2 homologous series to which the monomers in one belong. Okay, remember what we said, this one belongs to the carboxylic acids group. Carboxylic acids. And then this one becomes the alcohol group. Okay, so that's the homologous series to which they belong. So that's the end of this paper. I believe that you've learned something, and you've also seen how to properly answer the questions. So thank you for watching. Please endeavor to subscribe to the YouTube channel for more videos like this, and to share so that your friends can also learn from all that we do here. Thank you very much.